Hello all. In this video, we are going to correct the physics home sheet for the forces, Newton's second law and Newton's first law. In the first exercise, a car of mass m equals 1,500 kilograms initially at rest v0 equal to 0, is moving along a rectilinear and horizontal road as shown in the below figure. At time 0, a constant force of engine, which is called the traction force or tractive force, is applied to the car of magnitude 4,000 newtons during the first phase of motion. The force of friction is applied parallel to the surface of constant magnitude 2,500 newtons. Represent on a clear diagram the forces acting on the car. As you can see here in this diagram, that the forces are acting are the car's weight, the normal force on the wheels, actually the friction, and the force of the engine. Apply Newton's second law on the car to determine the acceleration of the car. So to determine the acceleration, we're going to apply Newton's second law, which is sigma F equals to ma. We write first all the forces, normal, weight, friction, and the engine tractive force equals to ma. Then we're going to project along either x or y axis. The motion is along x axis, not the y axis. Okay, along the y axis, the normal and the weight, they cancel each other. So the projection along the x axis, we'll just are lead with the friction and the engine. So the friction and the engine equals to ma. So we have only two forces along the x-axis, the friction and the engine. So we study the motion of along the x-axis, friction and the engine is equal to ma. Removing the vectors. After removing the vectors, we should put whether the force is in the negative or in the positive direction. How do we know? We take the positive direction as the motion of the car. So the car is moving to the right, so the positive is to the right. Fe is with the direction of motion of the car, so it's positive, while F, which is the friction, in all cases it's negative, is negative. So minus F plus Fe is equal to ma, mass times acceleration. Okay? So substituting the magnitude of the friction and the magnitude of the engine equals to ma, we get the acceleration as 1 meter per second squared. Deduce the nature of motion. It's of course UARM, since the acceleration is positive and constant. Acceleration is moving with the velocity, so v and a have the same direction and the same sign actually, and it's constant. Part 4, write the time equations of the car x and v, x of t and z of t, knowing that at time 0, x0 equals to 0. So since it's URM, so x equals half at squared plus v0t plus x0. Substituting the acceleration as 1 and initial velocity as 0 since it starts from rest. And x0 equals 0 is given. We get the time equation of position, which is x equals 0.5 t squared. While the vt equation, v equals at plus v0, acceleration is 1 and v0 equals to 0 since it starts from rest, so v equals to 1 times t, so v equals to z. Part 5, calculate the speed and the distance covered by the car after 10 seconds. So just substitute in these two equations time 10 seconds. Oh, sorry. So 10 seconds. So 0.5 times 100, which is 50 meters. Yes. And the velocity is v equals c, which is v equals 10 meters per second. Number 6, at time 1 during the second phase of motion, the force of the engine varies until it reaches a constant value, which is F prime. So we change the Fe, the force of the engine, where the motion is URM, knowing that the force of friction remains the same, which is 2,500. Calculate the value of the force. Now, since the motion is URM, so the Newton's law applied here is the Newton's first law. since the the car is moving at a constant speed, so the sum of the external forces acting on the object is zero. So sigma F equals to zero. This is Newton's first law. Newton's first law states that the object is either at rest or moving with URM. Okay, so similarly as before, normal weight, friction, and the engine, which is now F prime, the new force, but now are equals to zero. Also, we project along x-axis, either x or y. So we're here talking about the x-axis. We need to determine the F prime. So along x-axis, you have friction and F prime. Similarly, friction is negative, opposite to the direction of motion, same as here, and F prime is positive, but now they are equal to zero. So F prime is equal to F, which is 2,500. 6.2, calculate the distance covered by the car during 12 seconds of motion through the second phase. Now, the second phase, the car moves with URM, so that we can apply this equation, D equals VT, V, which is the speed, the final speed from the first phase, which we calculated here as 10. So V equals to 10 meters per second, and time 12 seconds. The answer is 120 meters. Okay, that's exercise 1. Now, in exercise 2, a car of mass 1,000 kilograms starts moving from rest. Yeah, this means that V0 equals to 0 on a horizontal road. The force of friction acting on it is constant of magnitude to 250 newtons. So the frictional forces are 250 newtons. The car reaches speed V final as 72 kilometers per hour. To convert it into meters per second, we divide by 3.6. So 72 divided by 3.6, which is 20 meters per second. Determine the traction force. To determine the traction force, you must apply Newton's second law. But before that, we should have the acceleration. We don't have the acceleration given in the question. So we have first to calculate the acceleration. How can we do it? Using time equations. So now we have the final velocity, we have the time, and we have the initial velocity is 0 since it starts from rest. So applying this equation, V equals 80 plus V0, we can calculate the acceleration. Now we can apply Newton's second law. Apply Newton's second law as in the first exercise. The forces are the force of the engine, or it's the tractive force. I called it in this equation, this exercise, traction, Ft. F, the frictional forces, F, normal and weight. Projecting along the x-axis, we have the tractive force and the force of friction. We have the force of friction minus 250, and the retractive we have to calculate the tractive force, which is now 450 newtons. So the attractive force is 450 newtons. Now, number 2, determine the distance traveled by the car during the 100 seconds. So the motion is, as you know, the URM, since there is acceleration. So to calculate the distance, we apply this equation, D equals half AT squared plus V0t. This is the same as X equals half AT squared plus V0t plus X0, or D equals. So substituting the acceleration as 0.2 calculated here, okay, 0.2 meters per second, and the time 100 seconds, and the initial velocity is 0 since it starts moving from rest. Distance is calculated as 1,000 meters. In part 3, the car now moves with constant speed, so it's URM. What traction force should the engine exert so that remain this speed? If the motion is URM, so we apply Newton's first law. Applying Newton's first law, we deduce that the attractive force is equal to the frictional forces. As an example, exercise 1, it's 250 newtons. In number 4, suppose that at some instant of time during the above URM, the driver switches the engine off without pressing the brakes. So the attractive force Ft is 0. So we only have the frictional forces along the x-axis. Calculate the time needed to stop the car. First, we have to calculate the acceleration. So the only force acting along the x-axis is the frictional forces, and the friction is of course negative, since opposite since it's opposite to the direction of motion. So calculate area. It's minus 0.25 meters per second squared. We need the time in order for the car to stop. So the velocity is equals to 0. The initial velocity is 20, which is 72 kilometers per hour converted into meters per second. The time here is 80 seconds. And the last question, calculate the distance traveled by the car from the instant the engine was switched off. So we have the time to calculate the distance. We use this equation, substituting the acceleration and the time, which is 80. We can calculate the distance as 800 meters. Stay safe and have a nice day. Bye bye.